Chemistry, the Central Science, Chapter 6, Electronic Structure of Atoms, Lesson 4. So in the previous lesson, we looked at our 4 quantum numbers, which tell you the address or the location of all of your electrons. So in a 1-electron system like hydrogen, if you are in the second energy level, that shell, your subshells are at the same energy level as well. So that's what this diagram here is showing, that regardless of the fact that you have different subshells, they're all at the same energy level because you only have 1 electron. When we get into a multi-electron system, then we start to see what we call degenerate orbitals. And so our energies are going to shift because now we've got electrons interacting with other electrons, our effective nuclear charge changes, we've got shielding that's happening, so things start to look a little different. So for all other atoms, what we end up seeing is that our 2p subshell is higher than our 2s, our 3p is higher than our 4s, and then we notice that 4s is above 3p, but less than 3d. So there is this specific way then that's going to show us how we are going to fill our electrons. We always start at the lowest energy and go to the highest energy. There are different ways to remember how these orbitals get filled. I'm going to teach you how to read your periodic table to know how to fill things because you're always given a periodic table. So in writing electron configurations, it's telling us where we find our electrons and how many electrons there are for each of our individual energy levels and subshells. So the Pauli exclusion principle states that no 2 electrons can have the same 4 quantum numbers. So you can have 2 electrons in every orbital, right? S orbital, each p orbital holds 2 for a total of 6. Each d orbital holds 10 or 2 for a total of 5. Each d orbital holds 2 electrons. There are 5 of them, which is a total of 10. Each f orbital holds 2 electrons. There are a total of 7. So that equals 14. So remember, in each of our orbitals, we have one that spins up and one that spins down. This allows for our electrons, even though they're sharing the same orbital, they have 2 different numbers. So the Aufbau principle is our building up principle. So if we look back at that last slide, we're always going to fill our lower energy orbitals before our higher energy orbitals. That's the building up principle. And then Hund's rule says that when you are in a specific subshell, like 3p, we know that we have our px, py, pz. When we go to do an orbital filling diagram, we're going to put our electrons in each one of those individual orbitals and then go in and pair them up. And this is because unpaired electrons are more stable. When we think about that bus ride, and we're going to get on a bus, and typically there's rows and there's 2 seats on either side. Human nature normally says, I'm going to go sit where there's nobody else sitting. I'm going to sit by myself first. Then a lot of people get on the bus, and then inevitably we have to pair up because most of the time we're not talking to strangers, right? Well, electrons work the same way. We're all going to go into our own little orbitals, and then we're going to get paired up when we have to. Why? Because electrons repel each other. So we want to minimize those repulsions. We can also maximize stability by maximizing our number of parallel spins that we have. So electron configurations, we start by writing our energy level first, which is our principal quantum number n, and then we represent our angular momentum quantum number, which is our L. So then we either have an S, P, D, or F. And then our superscript tells us how many electrons are present for this particular energy level with its subshell. An orbital diagram is used to show the electrons, and this is showing a spin-up electron for hydrogen. When I get to helium, which would be a 1s2 because I've added in a second electron, we would see that we would have a spin down. Then I continue to fill based off of my periodic table in terms of when I finish one row, I go down to the next row and I start again. So looking from lithium through carbon, this is in row 2, we notice that we have entirely filled S subshell, and then we have our 1s subshell, and then we have entirely filled 2s subshells over here, And then we notice that we are increasing then the number of electrons that we put into our p orbitals. When we look at this, we have to make sure that our exponents are going to add up to our atomic number. So beryllium has an atomic number of 4. That means a total of 4 electrons for a neutral atom. If you don't have a periodic table handy, I would suggest getting one now. And we're going to look at how we can label our periodic table so that we can learn how to write electron configurations just like that by using our periodic table, because you're always going to have one, right? So the first thing I want to do is denote my different blocks. So I have S, I have P, I have D, I have F. We'll notice here that the first 2 columns, your alkali metals and alkaline earth metals, there are 2 of them. This is your S block. Why? There's 2 electrons total that can go into an S orbital. If I come over here, I'll notice that my other main group elements, it's a group of 6 here, right? I have 6 elements together. Why? Because my p orbital can hold a maximum of 6 electrons. When I look at my Ds, I notice that there are 10 elements in a row in the transition metal block. Why? Because my D subshell can hold a total of 10 electrons. If I look down here at my lanthanides and actinides and I count, there are a total of 14 electrons or 14 elements in a row. That tells me that my F orbitals total can hold 14 electrons. Now, other things to pay attention to. If I am a main group element, which I'm either group 1 or 2, or I'm over here, so if I'm an S or a P, my energy level is my row number, straight up. So row 1 is 1, row 2 is 2, row 3 is 3, row 4 is 4, etc. Now, we can see here that the Ds are different, right? This is 3D, not 4D. Why is this 3D? Well, when I get into the 3rd energy level, I know that I'm allowed to have L values of 0, 1, and 2. 2 represents D. But these elements up here don't have enough electrons yet to put anything in the D orbital. So it shows up down here, and it's after we've filled our 4s that then we get into our transition metals, and that's where they're hiding away their extra electrons. So our Ds are a little different on your periodic table. I would make a note that this is 3D, 4D, 5D, 6D. Down here, when we get into our Fs, we'll notice that we're starting with 4F. Why? Because it is in your 4th energy level that you're allowed to have an F subshell to begin with. So when we remind ourselves, our actinides sneak in up here in row 6. So the first time you can have your F subshell is in energy level 4. However, we don't have enough electrons to fill it yet until we get down into row 6 with the inner transition metals. So it's like the transition metals kind of bury some of their electrons in these D orbitals, and inner transition metals bury a bunch of electrons in the F orbitals. And we'll notice then that for each of these transition metals, your valence electrons are actually in your S orbitals. So they're going to lose S electrons before they lose D electrons, which we'll talk about in the next chapter. So we use our periodic table. This is what we do. We learn how to read our periodic table like a book. We can pay attention to some electron configurations that are true for group numbers. So N, remember, is our row number. If you're a group 1, your outermost electron, your valence electron, would be NS1. Then we move to NS2 for group 2. For group 3, we have a filled S subshell, so that's NS2. And then group 3, we start off with our 1 electron in the p orbital, so NS2 and P1. And then we just keep increasing the numbers that we have in each of our p orbitals until we get over to the halogens, or to the noble gases, ignoring helium up here because it does not have an NS2 NP. That's just NS2. Helium is special. We can also look at some typical D elements, our transition metals, right? We all start off with a D1 here. Manganese group 7B will always have an electron configuration that ends D5. And zinc zinc's group 2b will always have a D10. And there's special stability that occurs when we have filled and half-filled d orbitals and f orbitals, because there's special stability that comes along when you can get a maximum number of paralleled spin electrons. So looking at your periodic table that you've labeled now with S, P, D, and F, let's write some electron configurations. So I look at silicon, I see that silicon has 14 electrons because its atomic number is 14. So I start at the top of my periodic table where hydrogen is. I go across that first row, I fill up my s orbital, 1s2. I go to the second row, I fill up my second s orbital with 2 electrons. I hop the pond of the transition metals and I get to my p orbital. Well, I fill that because now I'm at neon. I go to the third row, and I fill my s orbital. I hop the pond again, and then I see where silicon is. It has 2 places past where my p block starts, so it's a 3p2. So when I add up my exponents, I should get a total of 14, which I do, so 14 electrons matches. So this is your SPDF notation. We have a shorthand notation, which we look at the noble gas that's closest to our element but has fewer electrons. So we can see here that this electron configuration represents neon. And so we just put neon in brackets because this is completely filled. These are core electrons. They're not going to participate in anything. All of our subshells are filled, just like with neon. So then I just continue on. I've just substituted in. It's a shorthand notation. So over here for my orbital filling diagram then, I write out my neon because that's what already exists. And then I look at my subshells. I have a 3s, I label that. It gets 1 little line. And then I have my 3p. It gets 3 lines because there's 3 different orbitals, px, py, pz, where I can put electrons. So my 3s2 shows me up and down. My 3p2 says I have up and up. The reason why we do this is for Hund's rule. We want to have electrons by themselves before we pair them up. And then we also want all of our spins to be going the same direction to start. So you can be a spin up or a spin down person. I'm clearly a spin up person, but it doesn't matter as long as you have them all going the same direction. To start, we fill up, we fill up, we fill up, and then we go in and we match, right? Or we fill down, we fill down, we fill down, and then we go in and match. Oops. So technetium, atomic number is 43. So that means I have to have a total of 43 electrons. So I start at the top of my periodic table, row 1, 1s. That's where I always begin. I fill my first row, 1s2. I fill my second row, 2s2, 2p6. That takes me to neon. I keep going until I hit the element that I'm trying to write my electron configuration for. So I go to row 3. I filled my 3s2. I fill my 3p6. That takes me to the end of the noble gases. There. I get 4s2, and then I go through my transition metals. That first transition metal row, remember, is 3d. I fill it all the way up, so a total of 10 electrons. Then I get into my 4p6, which hits krypton. Still not done because I haven't reached the element that I want to. So I go down another row. I see that that starts my 5s2. And then I go to where technetium is. I count 5 spaces down. That's why this is 4d5. So if I add up all of my electrons, I have 10 here, plus another 10 is 20, plus 10 is 30, 6, 38, 43, and it matches. So we remind ourselves, right, that 1s2 is helium. If I've got through 2p6, that's neon. If I go through 3p6, that's argon. If I go through 4p6, that's krypton. If I notice here, these are completely filled subshells, so I abbreviate it then by writing krypton in brackets, and then I include the rest of my electron configuration. So going over here then, I note my noble gas that I have krypton, and I've got my these are backwards, so this should read 5s and 4d. So this 5s we see is completely filled with 2 electrons. And then I've got 5 electrons in my 4d, so remember these are backwards. So I go spin up on all of these, everything is unpaired first, and then if I had more, I'd go back in and pair them up. So this tells me that I have 5 unpaired electrons. Right here, there's 2 unpaired electrons. All right, copper. So copper's atomic number, right? We look at our periodic table, we see it's 29. So I do my electron configurations the same way I start all my other ones. At the top of the periodic table on the left where hydrogen is, I go through my first row, I fill it up. I go through my second row, I fill it up. I go through my third row, I fill it up. I haven't gotten to my atom yet that I'm interested in. Now you'll notice here this is an anomaly, right? Because normally we would write 4s2 3d9. Well, copper actually has an electron configuration of 4s1 3d10. And you can look over here at the orbital filling diagram to see why. So here I've got a completely filled d subshell. So to have a completely filled d subshell is more favorable than having an s subshell filled and then one d orbital not filled. So there's special stability that's conferred upon atoms when we can have half-filled d subshells or filled d subshells, and then we can fool around with the s electron. So the s orbital, it holds 2. We can take an electron out of there and put it in a different orbital for special stability purposes. But our electron configuration works the same way. I look here, I have 18 electrons that are completely filled, or sorry, that's 10. Here's my 18. That gives me argon, which is why I wrote that in brackets. And then my 4s1 3d10 takes me to copper. Why does this still copper and not zinc? Because if I add these up, 10, 12, 18, 19, 29, I see that the total number of electrons is 29. Doesn't matter where I put them. Here, this is just showing however many electrons I have, that is my atomic number. We can talk about excited states where we can actually promote electrons to a higher energy level. Doesn't change who you are as an atom. It's just saying, hey, I've got some electrons that are excited. So looking back at some subshells and quantum numbers and determining how many electrons that we can have. So the maximum number of electrons that can occupy each of the following subshells. So what we're interested in here is not the principal quantum number, because that just tells you your energy level, which then can tell you the different types of L values you can have, right? But your subshells are looking at the letters. So in a D subshell, regardless of what energy you're at, the total maximum electrons would be 10, because you have 5 different d orbitals. For a p subshell, you have 3 p orbitals. 3 times 2 is 6. For an s orbital, you only have 1 of them, so 2 electrons. For an f orbital, for an f subshell, you have 7 orbitals, each holding 2, so 7 times 2 is 14. So regardless of your energy level, this is the maximum number of electrons that each of your subshells can hold. So now if we actually bring some quantum numbers into it, if n equals 2 and m sub l equals 0, once again, the energy level is only determining the number of subshells that we can have. So I look here at m sub l and it says that it equals 0. Well, this is just showing me I only have one particular orbital, so that's 2 electrons. Once again, energy level only tells me the determination of my L and M sub L values. So when L equals 2, that tells me that I have a D subshell. Maximum number of electrons in a D subshell can have 10 electrons. So the maximum number then would be, I'd have 10 different electrons with these 2 numbers in common. N equals 6, L equals 3, M sub L equals 1. So once again, when we get an M sub L designation, that tells me I'm an orbital, and in a specific orbital, I can only have 2 electrons. So that's my 2 electrons here. So basically what this is saying then is I could have a 6, 3, negative 1, 1/2. I could have a 6, 3, negative 1, negative 1/2, right? Those would be my 2 different sets of quantum numbers. N equals 4, L equals 1. So once again, at this energy level, L equals 1, which means I have a p subshell. In a p subshell, I know that I'm allowed a maximum of 6 electrons because p subshells, there are 3 individual orbitals, each holding 2 electrons. All right, last thing to practice here is if we're given an electron configuration and we want to figure out the element. Well, as we spoke earlier, or as I spoke to you earlier about this, your exponents tell you the total number of electrons. So I'm just looking at an electron count. Neon, atomic number 10. I add 2 and 3 to it to get 15. So 15 atomic number is phosphorus. When I look here, how do I know that these are unpaired electrons? If you draw your orbital diagram, I know that I'm going to put each of these electrons into their own individual space first. So 3 unpaired electrons. Helium has 2 electrons, plus 2 plus 5 gives me a total of 9, so that atom is fluorine. If I go through here, I have a p5, which means I have 3 electrons that I would write down unpaired at first. Then I go in with my next 2, I pair them up. So I only have 1 unpaired of electrons. So how many electrons for argon? That would be 18 because it's its atomic number. 18 plus 2 is 20. The atomic number of 20 belongs to calcium. Because my s orbital is filled, I have 0 unpaired electrons. So when you look at your periodic table, if you're a group 2 or you're a group 8, you will have 0 lone electrons, meaning you will have no unpaired electrons. Everything is paired. If you are like zinc, and in zinc's group, you will also have 0 lone pairs of electrons. And just a little side note, it is the fact that elements have unpaired electrons that allows them to be magnetic. So diatomic oxygen is actually magnetic because it has lone pairs of electrons. So if you freeze oxygen, make it a solid, you can pour it between a magnet and it sticks. All right. So continuing on here, krypton has a total of 36 electrons. So 36 plus 2 is 38. We add 10, 48. We get to cadmium, 0 unpaired electrons. Why? Because my D subshell is completely filled and my S subshell is completely filled. And lastly here, we have argon, which is 18 electrons. Plus 1 is 19. Plus 5 is 24. Remember, it doesn't matter that this isn't an S2 3D4. This is special stability because we've got all unpaired electrons then. Everybody's in their own row on the bus. So once again, what do we do here? 18, 19, 24. So chromium's atomic number is 24. Total of 6 unpaired electrons.